Well, this lecture we are going to introduce a definition of a special kind of sequence, which is series. Let's first look at our number a third, or as a decimal 0.33333 forever. We all know that our number system has place values, so the first 3 in the tens place means 3 over 10. Then the second 3 in the hundredths place means 3 over 3 hundredths. And then the third 3 in the thousands place means 3 thousandths. Then, of course, 3 10,000, etc. So you are having a sum of infinite fractions. And here the ... which is really important, it means the sum doesn't end there. It goes on forever. Then we can, with this example, I'm going to tell you what all this definition and terminology means, okay? So if we try to add the terms of an infinite sequence, an, we get an expression of the form a1 plus a2 plus an, a3, all the way to an, and they keep going. So you can imagine series is the sum of the first n terms of a sequence. So every time the series gets one more term, and you have the finite sum gets one more and one more. At the end, when you add the sequence, all the terms of a sequence together, that's your series. Okay, so a series is a sum of infinite sequence, essentially. And yeah, so we can just say it's series, or if you want to emphasize that it is infinite, you can say it's an infinite sequence, infinite series. And it's the sum of all the terms of a sequence. So you can denote it by saying, instead of the notation that I'm having all these terms, or I'm having all these terms from n to infinity, here pretty much you are saying I'm adding them up. If you want to emphasize that you are having from 1 to infinity, or in the case it's not from 1 to infinity, maybe you are adding them from n equals 5 to infinity or n equals 0 to infinity, you want to indicate them, okay? Otherwise, by default, it's from 1 to infinity. So go back to our a third case, or the 3 tenths plus 3 hundredths. I want you to look at this because this is really the sum, okay, of infinite sequence. So what are you having? You are having a1 is 3 over 10, a2 is 3 over 10 squared, which means an is 3 over 10 to the nth power, so that your a1, a1 is 3 over 10, a2 is 3 over 10 squared. Again, I don't really have room for it. So our sigma am will be, n from 1 to infinity is the sigma n from 1 to infinity, 3 over 10 to the nth power, and when 10 equals 1, that's 3 tenths, 10 equals n squared. n equals 2, you have 10 squared. N equals 3, you have 10 to the third power, and it keep going. Okay, so that's our series, the one I circled. Now, given this series, or in general, given a series sigma an, we can talk about the first n terms. Well, you can't look at infinite terms at the same time. You always have to stop somewhere, right? So the first n terms give you a partial sum, which is Sm. So S1, look at this notation. Okay, I'm trying to show you how this notation works. So when S equals 1, this is 1. You're having I from 1 to 1, A, I. And that would be I goes from 1 to 1, which means it only go one place, 1, A1. Now S2 would be I goes from 1 to 2, AI, and that would be I being 1 in here and I being 2, in the expression after the summation sign. Similarly, S3 will be the first three terms added up together. AI, which is A1 plus A2 plus A3, etc. And of course, when you let n approaches infinity, you are really just adding up all the terms, which means the limit as n approaches infinity of S of n is just S, which is the sigma. Okay, if the sum converges, then here you are, they are the same. So what I'm trying to say here is the limit as n approaches infinity, as n equals the sum n from 1 to infinity an. They are the same. So if this sequence, this is a sequence, right? We have already defined. If this sequence converges to a number, then our series is convergent. And if the limit of Sn diverges to infinity, our series diverges to infinity the same way. And if it does converge to a number, the number is the sum of the series. Okay, those are, again, terminologies. Now let's look at this series that we have been talking about a little bit closer. What is the sum? Does it converge? We only know this series is well defined if it's only if the limit of the sum sequence converge. The series makes sense, represents a number. Otherwise, it's divergent, which means it's not really a number. So let's see. The first n terms, we already had an equals 3 over 10 to the nth power, right? So our first n terms would be 3 over 10 for n equals 1, 10 squared for n equals 2, all the way to 10 to the nth power for n. Now, if I multiply a tenth to the sequence, I am going to multiply a tenth to all of them, right? When you multiply tenths, you are really multiplying 1 over 10 to each of the fractions, which means you are multiplying 10 to each of the denominators, which means you are raising the power of 10 by 1. So 3 over 10 times 10 give you 3 over 10 squared. Then 3 over 10 squared times 1 over 10 give you 3 over 10 to the third power plus ... and then the 3 over 10 and minus 1 would give you the 3 over 10 to the n, but 3 over 10 to the nth power multiplying by a tenth will give you another term. So pretty much, that's how you get it, by multiplying a tenth, and multiplying a tenth. Somewhere here, it goes to this term. As you can see, they are the same, and they are the same, and actually everywhere here between 3 over 10 squared and 3 over 10 to the nth power, they are all the same. So I can go ahead and subtract. What would I have? I will have 1 minus, let me just write Sn minus a tenth Sn on the left-hand side, and on the right-hand side, all the middle terms are cancelled. I only have this 3 over 10 from the top minus 3 over 10 n plus 1 from the bottom. This would be 1 minus 1 tenth Sn. I factor out the coefficient, and on the right-hand side, I can factor out 3 over 10, 1 minus 1 over 10 to the nth power. Dividing by this coefficient, I have Sn equals 3 tenths, 1 minus 1 over 10 to the nth power over 1 minus 1 over 10. Okay? Now I'm going to let n approaches infinity. So the sum n from 1 to infinity an is the limit as n approaches infinity of Sn, which is the limit as n approaches infinity 3/10 times 1 minus 1 over 10 to the nth power over 1 minus 1 over 10. As n approaches infinity, 10 to the nth power is infinity, and 1 over infinity is 0. So I'm really just having 3 over 10 over 1 minus 1 over 10. And I want you to observe this is the first term in your series over 1 minus the rate. Like every term you multiply by a tenth, right? Which is called the ratio. But of course, let me work it out. I multiply a 10 top and bottom, or I have 3/10 over 9/10. I'll do the multiplying 10 top and bottom. So 3 over 10 minus 1, which will be 3 over 9. Or a third. If you remember, we started by saying 0.3333 is a third. Let's write the decimal form into the series, right? So we go back to where we started, a third. But more importantly, the sum is first term over 1 minus the common ratio. Actually, as I put here underneath, this kind of series is special. They are called geometric series, where pretty much you are having a leading term, and then each term you multiply by an r from the previous term. So AR, R squared, R third, R fourth, all the way to the end, where, of course, the leading term can't be 0, otherwise the whole sequence is 0. There's no point to adding them up. And the multiplier you are having is called common ratio, and normally we denote it by R. And if R is less than 1, which means every time you are multiplying, well, you keep multiplying the same number to the previous term, right? So if the number you are multiplying has an absolute value less than 1, then the series converge to first term over 1 minus common ratio, A over 1 minus R. And if the absolute value of the common ratio is 1 or higher, the geometric sequence is divergent. Notice that you are having, because our first term is A, so our second term would be AR. That means you need to be very careful with this exponent when you are writing the sum form. When you are writing the summation form, it has to be AR n minus 1. Okay, so the general form. If you do list them out, it's very easy. The first term times 1 minus the ratio. But if you are dealing with this sort of general form with n and the summation, you need to make sure you have the power n minus 1 inside your summation. Now let's see examples. So we are seeing whether these two, well, I already told you geometric series is convergent or divergent. If it is convergent, you are going to find its sum. And if it is divergent, you are going to say why. All right. So my first sequence, I'm having sigma n from 1 to infinity. Remember, I need AR n minus 1 in the summation. So first of all, let me get the 7n plus 1 as 7 times 7 to the nth power, 10 to the nth power. So this will be 7 times 7 over 10 to the nth power, and then that would be 7 times 7 over 10. 7 over 10 n minus 1. You need that n minus 1 power, okay? And that is 49 over 10. 7 over 10 n minus 1. I still think, in a way, it's easier if you write like a bunch of terms and see. Our first term would be n equals 1, which is 7 squared over 10, plus n equals 2, 7 third, plus 10 squared. You will see, the first term is 7 squared over 10, or the 49 over 10, and meanwhile you are multiplying your 7 over 10 on top of it for the second term. It might be easier. Anyway, our common ratio 7 over 10 is less than 1, so the series is convergent to the first term, which is the outer part, over 1 minus the common ratio. So this gives me 49 over, if I multiply 10 top and bottom, 10 minus 7, or 49 over 3. My second example, I'm having 1 plus 1 half plus 1 fourth plus 1 eighth. I didn't give you the general form, but I hope it's pretty obvious. This is 1 plus 1 over 2 to the first power plus 1 over 2 to the second power, 1 over 2 to the third power, etc. So this will be n from 1 to infinity. 1 doesn't matter, but if you want to, 1 times. What's the common ratio? You are multiplying 1 half to the nth power. So the first term is just 1. The second term, n equals 1, right? And then, n minus 1. So the first term you get just 1. Second term you have 1 times n minus 1, which is 1. So 1 over 2. So here, 1 is the leading term. This is A, this is R. And our R equals 1 half is less than 1. Convergent, then we can do A over 1 minus R, 1 half. And this is 1 over 1 half, or 2. Okay, this is how we find the sum of geometric series if the common ratio has absolute value less than 1. Now you can pause the video and try practice number 1 and number 2. Well, other than geometric series, there are other kind of series which you sort of have to decide how to deal with them to show they are convergent or divergent on sort of case-by-case situation. So let's look at our first example here. Same thing, we want to decide convergent or divergent, and we need to justify the reason. The first one is a really tricky one, but I want you to see it. The sum of all the terms 1 over n times n plus 1. So what you need to do with this particular fraction, or sometimes you can have a 5 if you want to. You can pull that number out anyway. Is that you are going to say, oh, this is actually, the 1 is actually n plus 1 minus n over n times n plus 1. Then you do the fraction minus the fraction. Okay, so this actually equals from 1 to infinity 1 over n minus 1 over n plus 1. Well, maybe let me write it out for you. Is n plus 1 over n times n plus 1 minus n over n times n plus 1, where you cancel the common factors and you get from n to 1 to infinity 1 over n minus 1 over n plus 1. So each term, it's a difference. And when n equals 1, you get 1 minus, let me keep the limit, n approaches infinity, the n equals 1, you get 1 minus 1 over 2. n equals 2, you get 1 over 2 minus 1 over 3, plus the third term, 1 over 3 minus 1 over 4, etc., all the way to 1 over n minus 1 over n plus 1. That's the partial sum for the first n terms. Then we let n approaches infinity. But notice that you are minusing 1 half plus 1 half, minusing a third, plusing 1 third, minusing 1 fourth, and it will be added in the next parentheses all the way to minus 1 over n plus 1 over n. So actually what's left after cancellation is just 1 minus 1 over n plus 1. And as n approaches infinity, this is 1 minus 1 over n, which is 0. So the whole thing is 0. Oh, sorry, it's 1. 1 minus 0 give you 1. Okay, this is a pretty tricky case too. So somehow each term of your sequence is a difference, and the terms in the consecutive terms of your sequence cancel each other. Now, second example, the sum of n squared. So what are we having? We're having 1 squared plus 2 squared plus 3 squared plus 4 squared. Keep adding. You keep adding, it gets higher and higher, right? So actually it goes to infinity. I think it's quite obvious, but how can you justify it? You can simply say Sn is 1 squared plus 2 squared all the way plus n squared. It's a huge number. How big it is, I don't know, but it's definitely bigger than n squared. So the limit as n approaches infinity of Sn will be greater than the limit as n approaches infinity of n squared, which is already an infinity. The only thing that is greater than infinity is infinity itself. So it's divergent. And here we have the theorem, which pretty much is what we sort of observed in our second example. If a series is convergent, the terms, the an that you're adding up, has to converge to 0. You have to keep adding smaller and smaller stuff, positive or negative, okay? So the limit of the term itself has to be 0, so that, at the far end, when you add so many terms, it doesn't matter. Or you add one more term or one less term, it doesn't matter, because they are all zeros you are adding, so the sum doesn't move at all. If a series is convergent, the limit of an has to be 0. And then the backward is also true, which is if the limit is not 0, if the limit of an is not 0, which means it could be not exist or exist but not equal to 0, then the series is divergent. The series cannot be convergent. Okay, so that's a very useful theorem to decide whether a function, to decide that a series does not converge. It doesn't guarantee it will converge, but it will guarantee you the series does not converge. Now the third theorem is saying pretty much you still have the nice addition, subtraction, and multiplication rules with series. Actually, it is also true for multiplication. When you are adding, subtracting, and multiplying, even dividing series, if they converge at the first place, then you can do the all these operations sort of term by term. It's hard to really do it with division here, but I'm not sure if I'm going to tell you what it means later, but it's true for multiplication for sure, that you can just use it. Division is a little bit complicated, yeah. And the harmonic series, which is really important, but here I will just include it as a remark because I don't want to really show you the whole proof. Well, the idea is 1 is greater than 1. Well, at equal to 1, 1/2 is 1/2, then a third and a fourth is greater than 2 copy of a fourth, which is a 1/2. Then you look at 1/5 all the way to 1/8. That's greater than 4 copies of 1/8, which is another 1/2. So pretty much you look at the next number will be 1/16, and you have 8 fractions that is at least 1/16, add them up another half. So you are keep adding 1/2 forever, which make it divergent. But anyway, yeah, I'm not going to do the whole proof. Just remember that harmonic series, which is the sum of the 1 over n, the integer, the reciprocals of integers, when you add them up, is divergent. the last two examples for today. First, well, same thing. We're looking for this limit if it's convergent, and we're going to say why it's divergent if it's divergent. Number 3, we're looking at the sum of 2n minus 1 over 5n plus 2. Now you need to look at the limit first. As n approaches infinity, the limit actually is 2/5, not 0, not convergent. The thing you're adding up does not head to 0. So it's divergent. The limit of an has to be 0 to make the series convergent. It's not sufficient, but it's necessary. The fourth example, I'm having a sum on the numerator. So knowing that the series of the sum of two series is the series of, the sum of according terms, you can write it as two fractions 2n over 4n plus 1 over 4n, where each of them is a geometric sequence 2n over 4n. So I'll do 1 over 2n, right? Plus 1 over 4n. That is series from 1 to infinity. The first term is 1/2. Then I have 1/2 and minus 1 plus 1/4 to the n will be 1/4 times 1/4 and minus 1. So a, r, and minus 1. A, r, and minus 1. Okay, so this equals to 1/2 over 1 minus 1/2 plus the first term, 1 minus the ratio. And if you work it out, this multiply 2 top and bottom, this will be 1/2 over 2 minus 1 plus times 4 top and bottom, 1 over 4 minus 1. So 1 plus 1/3 or 4/3. That's it for this package. Now you can finish the practice 3 through 6.